Hi, this is Robert Bolaños. In this video, I will be measuring the input impedance of a power supply that I designed. So one can ask, well, why measure the input impedance? Okay. Well, one of the reasons would be if you have a system of multiple supplies. Okay. If the input impedance of one or maybe several of your supplies are low enough, it can cause your voltage to be loaded. Okay, what does that mean? Well, your voltage at your input bus can start to decrease. Okay, so it's going to start going down, or it can sag. Okay, and typically you don't want that. You want a good, stable supply, bus supply that doesn't change. Okay, so that's one of the main reasons. Another reason is if your input bus is loaded or has a certain impedance, you will have a tendency of oscillating. Okay, and that's something that happens, and used to happen in the early days until Mr. Middlebrook figured out why he was doing. Now if you have an oscillation, then what you're doing is you're violating the Middlebrook criteria. And basically, the Middlebrook criteria is really the oscillation rather, is a interaction between the filter and your converter. Okay. And typically it's the input impedance. How? Well, the output impedance, or at least the Middlebrook criteria states that the output impedance of the filter, okay, this would be the filter and this would be the output impedance of the input filter, has to be much less than the input impedance of the converter. Okay, and this would be the input impedance. Okay, so if you violate that, then you're going to have oscillations. Okay, another reason that I'm doing this video is that I recently bought the Bode 100 from Omicron. It's a FRA and it's also a VNA. So the last 2 weeks I've been playing with it, learning how to use it, and this video will show some of the things that I have learned in using the Bode 100. Okay, here you have the Bode 100 on the left. It's a frequency response analyzer, and it is also a vector network analyzer. Okay, so these are the two pieces of equipment that you need to measure the input impedance. Now on the right, you also need a line injector, and the line injector that I'm using is the Picotest J2121A line injector. So using these two will allow you to do a measurement of the input impedance. Okay, and I want to add one more thing, that these two are used to measure the input impedance, but there's another important measurement that you can do with this. You can do the PSRR measurement, and there's a third. You can also measure the negative resistance of a power supply. PS, power supply. So with these two, you can do these three measurements. Okay, so before I make the measurement, I want to talk a little bit about the Bode 100. It's a very versatile piece of equipment. As you can see here, these are all the things that you can do, and it's a piece of equipment that that every power supply engineer should have in his lab. So starting on top, one of the first measurements that one will do is measure the gain and phase. So when you're doing the phase gain and phase, what you're really doing is you're measuring the stability of your power supply. Okay, so this is very important. It's a must. Usually the gain and the phase are specified by your in your requirements and your specifications. A second is the input impedance of the power supply, and I'll be showing that in this video. And the reason that we do that is also related to the stability of the power supply. A third is the output impedance of a power supply. This is a very important parameter to measure the output impedance, because once you measure the output impedance, then you're able to do a PDN analysis. Okay, and PDN is power distribution network analysis. So this is something that has gained a little more acceptance, and more power engineers are doing this type of analysis. So this is very important. Okay. Next one is the negative impedance, or specifically negative resistance. Okay, so this is typically without the input filter. Okay, so I'll be doing a video showing how to do that as well. Next one is the PSRR. Another name for it is the audio susceptibility. And basically what you're doing is you want to know how much a signal is attenuated. So basically, if you have your power supply and you're going to feed a input voltage of Vn, and if you add a AC signal to it, let's say a sine wave of some kind, and that sine wave can represent noise, then you measure your V out and you measure how much of that got through. Okay, so basically you want to see how much is of the input signal shows up at the output and how much attenuation you have. So the greater the attenuation, the better. Okay, so the next thing that you can do with the Bode 100, which it does it very, very well, is that you can measure the ESR, the equivalent series resistance. You can measure your inductance of your inductors or your magnetics. You can also measure the self-resonant frequency resonance. Once you know the resonant frequency and you know the inductance, then you can calculate the parasitics. And to do that, you use this formula. It's 2 pi f squared times what you measure. Okay, so that would be the f is the resonance frequency, and L is the inductance that you measure. Okay, very important. Okay, here is another that you can do. Another task or thing that you can do is characterize your power supplies, or I'm sorry, your capacitors. Okay, so on your capacitors, you can measure the ESR, you can measure the capacitance, and then you can also measure your ESL, which is the equivalent series inductance. Very important. We used to neglect the ESL, but now with FPGAs, and this kind of ties into the PDN. FPGAs are operating with voltage of 1.2 volts and currents of maybe 50 amps or higher. Now you cannot neglect the ESL. You have to account for that. You have to measure it. Okay. So that's something that you have to do now. Okay. And going back and how that ties in, like I mentioned, on a PDN, now that the FPGAs are working at such a low voltage, if you have a power supply, well, you're going to have a trace. The trace is going to have some resistance, and if it goes through vias and the trace, you're going to have some inductance, and then there's some board parasitics, capacitance, and then your connectors and so forth, and then you'll have your bypass capacitors. So all of this is a network, okay? And then by the time it comes to your FPGA, you actually have a series and parallel connections of capacitors, inductors, and capacitors. So it's a network, okay? And what you want to do is you want to measure basically at your FPGA, and you want to measure the impedance, okay? So that's what you're doing with a PDN. And what you want is you want a flat response, as flat response as possible and as high as possible, okay? That way, if you have any resonance or peaks, you could end up with some rogue waves, okay? So that's a very important subject, and that's another video that I'm hoping to do. Okay, here we have the Bode J2121A line ejector, and I'm going to talk a little bit about how it's used and how it works. Okay, so first of all, you put your input voltage on the left side. There's some banana jacks, and this would be your V input. In my case, I'm going to be using 12 volts. Okay, and that 12 volts is then routed, and it goes into this L1. I believe it's either an amplifier driving a transformer. So that 12 volts goes through L1, and then it exits on the right side. Okay, and typically this would go to your power supply. Okay, now the 12 volts comes in, and you got 12 volts coming out, powering your supply or whatever voltage you set, plus there's going to be a AC signal. Okay, where does this AC signal comes? Well, it comes from this side. If you notice, there's an oscillator there. It comes out through here. So this one, this BNC, you connect to your Bode 100, and you connect it to the output of the generator. So the generator is going to put a wiggle, sine wave. That wiggle goes in and will travel along with the 12 volts. Okay, and typically, since you're doing a impedance measurement, okay, you're going to be doing a V divided by I measurement, and that should give you resistance in ohms. Okay, so at this point, at the input of your power supply, you're going to connect to your Bode, Bode 100, and you connect it to channel 2. Okay, and that's going to measure voltage. Okay, and typically you would put a external current source, but in this case you don't need a external current probe, because there's one already built in. That's what makes the J2121 special. It's got this current probe already connected in there, which makes the measurement much easier. Basically, that current probe, the output comes out through this BNC on the right side. That goes to your Bode under. Okay, let me correct right here. Okay. It's a Bode 100. So it goes to the Bode 100, and this is your current measurement. Okay, and you're going to connect this to channel 1. Okay, so basically you make your voltage measurement and you make your current measurement, and then the Bode does a calculation, and then they'll display it basically, like I said, in ohms. Okay, so that's the way the J2121 works. Okay, here you see a schematic representation. You can see the Bode 100 up here. Okay, and in my case I would be putting 12 volts. The 12 volts will go into the J2121, and then 12 volts will come out, which is the DC, and then the Bode will inject the signal, which is an AC signal, and then that is modulated, and then basically is right in the 12 volts. So you're going to have a 12 volts plus an AC signal. And again, here you can see this is for voltage measurement, and then the internal current source is the current measurement. Okay, so basically that's the way you hook it up. Now before you hook it up, you want to make sure that it's calibrated, and again you can see it's exactly the same connection. Okay, so the only thing is, instead of putting the power supply here, you actually connect a precision 1 ohm resistor. Okay, then once you run the calibration script or file, then you can do a measurement with the 1 ohm resistor, and this will be in ohms and frequency, and then you run a measurement and you should get a 1 ohm throughout the frequency range, okay, that you're sweeping. So it should be nice and flat. So that's how you know that it's calibrated. Okay, so that's the way you calibrate the Bode 100. Okay, so now that we know how to hook it up and measure the impedance, then we'll get on with the measurement.
This is the input impedance measurement. Here we have the Bode 100 configured to take a input impedance measurement of the power supply. Okay, here's the power supply. And to make a impedance measurement, we have to supply 12 volts, okay? And that is going through this Picotest injector. This is the J2121A line injector. 12 volts is fed into the injector, and a signal is injected into the line, the 12 volts that is routed through the injector. That 12 volt is modulated with a signal, and that signal travels to the input connector of the power supply. Now that signal comes from the Bode 100 shown here. Okay, so that signal is being injected. It modulates the 12 volts. Okay, and then we connect channel 2 to the input. Okay, so we're going to measure that wiggle. Okay, so now the only thing that we need to do is we need to measure the current. So if we do a voltage divided by current, then we get units of ohms. And the way we do that is this Pico injector and Picotest injector has a current sensor that measures the current coming through the 12 volts. So that signal, the output, which is the iSense or iMonitor, that is routed to channel 1. Okay, so this is voltage, this is current. So they divide it and we get impedance. Okay, so now we go to the computer and we start taking the measurement.
Okay, here you have the Bode analyzer suite, and we're going to do a input impedance measurement. So we'll go ahead and start, and okay, so here we have the plot or the graph. So we're going to measure the input impedance, and this is before the input filter. In other words, this is the whole power supply. This includes the input filter and the power supply itself. Okay, so we're going to measure from 10 hertz all the way to 40 megahertz, and we'll put a bandwidth, meaning a filter of 300 hertz. So we're basically ready. Press continuous measurement, so we'll continuously will sweep across the frequencies. Okay, so here we have the red plot. This is, if you notice, it's units of ohms. Okay, and then the blue is your phase. Okay, so I'm interested in the ohms, so I'll take off the phase, and looking at this a little bit more closely, and let's see if we can get this a little bit more. And let me go up to, okay, so if we look, where is my cursor? Oh, there it is. Okay, so if we look at about 10 hertz, we see that the impedance is 20, 30, 40, 50, about 60 ohms. Okay, and then it drops to, at 100 hertz, just above 10. So actually we can actually put a cursor here close by. It's 12.12 hertz. Okay, and then we go to 1 kilohertz. Actually we can even type in here 1. Okay, it's actually 2.2, and then we'll type in 10 kilohertz, and now the impedance drops to 1.26, so forth, and it stays about there. And then if you notice at about 400 kilohertz, then you start increasing in impedance. Okay, so let's see what's happening. So since we're measuring at the input of the power supply, which has a input filter, the first component that it's going to see is the series inductor. So the series inductor at low frequency doesn't have enough impedance. Basically it's very low impedance, and there's a capacitor that is connected to it to ground. So what you're seeing here is this is the impedance of the input capacitor. It's the dominant. Okay, and then as it sweeps, then you have the ESR of the capacitor and a little bit of the probably the control reducing this. So this would be the ESR of the capacitor, and then as you have this input or this impedance rising, that is the series inductor, where it then becomes the dominant impedance looking into the power supply. So here you have a nice representation, a good measurement. It shows that you have a pretty low impedance at these frequencies between 10K and about 200 kilohertz. Okay, so that's the way you take the measurement. Thank you for watching.